Hi, I'm Woo-Jae Kim, presenting our highlights paper, Feature Separation and Recalibration for Adversarial Robustness. We will first provide a 1-minute preview of our work. Deep neural networks make decisions on an image by learning their feature representations. Adversarial attacks, however, disrupt the feature activations of images, and these disruptions are passed down the network and ruin its final decision. To solve this problem, existing defense methods simply deactivate or suppress these disrupted activations. However, this approach can lead to loss of potential discriminant cues regarding the target object and limit the model's ability to make correct predictions. Therefore, we instead propose to restore useful cues from these disrupted activations that are otherwise neglected. This additional useful information will better guide the model to make correct predictions under attack. Based on this idea, we propose feature separation and recalibration module that restores useful cues for predictions from non-robust features responsible for model mispredictions under attack. Now we will present our paper in more detail, starting from our proposed method, feature separation and recalibration. As mentioned in previous slides, the goal of our research is to restore useful cues for correct predictions from disrupted activations. While suppressing or deactivating them may reduce their detrimental effects, it can also lead to loss of potentially useful cues that have been exploited in natural images. Restoring these useful cues will provide a richer amount of information regarding correct predictions. We propose the feature separation and recalibration module, which is designed to recalibrate disrupted feature activations and restore useful cues for predictions. We designed the FSR module as the two-step process. Separation step extracts non-robust features responsible for model mispredictions, and recalibration step restores useful cues from these activations. This module can be inserted to any CNN model, and it is trained along with any adversarial training technique in an end-to-end manner. The goal of the separation step is to separate the input feature F into the robust feature F+, which consists of activations that provide useful cues for correct predictions, and the non-robust feature F-, which consists of activations that are responsible for model making wrong predictions. To separate the feature map based on the relevance to model making correct predictions, we designed the separation net to learn the robustness of each activation. From the input feature F, the separation net outputs two masks M+, and M-. Positive mask M+ max out the non-robust activations that are responsible for mispredictions, and the negative mask M- max out the robust activations responsible for correct predictions. Then we apply each of these masks on the input feature to generate the robust feature F+, which consists of activations that provide useful cues, and the non-robust feature M-, which consists of activations that lead to mispredictions. To better aid the understanding of our module, we visualize the masks learned by the separation net and the resulting feature maps. The intermediate feature map of the adversarial image wrongly activates object-irrelevant region of the image due to disruption, which would lead the model to misprediction. The separation net learns the max based on the robustness of each activation and extracts a robust feature with activations relevant to correct prediction, and the non-robust feature with activations irrelevant to correct prediction. In order to train the separation net to generate correct max based on the feature robustness, we attach an auxiliary classifier after the two features F+ and F-. Based on each of their output prediction losses P+ and P-, we designed the separation loss. The separation loss encourages the positive max to emphasize activations responsible for correct predictions, and the negative max to emphasize activations responsible for wrong predictions. Based on the separated features, conventional methods simply suppress these non-robust activations. This approach can neglect potentially useful cues in these activations, which will degrade the model's ability to make correct predictions. Thus, based on the extracted non-robust feature, we propose to instead restore useful cues from these disrupted activations through recalibration. This recalibrated feature will capture additional useful cues for correct predictions that are otherwise neglected through suppression or deactivation. We add this recalibrated feature, F-, with the robust feature to form the final output feature, F-, which is now passed back into the subsequent layers of the model. In order to restore useful cues from the non-robust feature, we designed the recalibration net R, which learns the recalibrating units. We applied the negative mask on the recalibrating units and used them to recalibrate the non-robust feature and to generate the recalibrated feature F-. Again, we visualize the feature maps upon recalibration. The recalibrated feature recaptures useful information for correct prediction, which in this case is the head of the B, from the disrupted non-robust activations. Note that this is the information that has not been captured by the robust feature. Thus, simply suppressing the non-robust activations would lead to loss of this important information. Through recalibration, we provide the model with richer amount of information regarding correct prediction. To train the recalibration net to correctly restore useful cues from non-robust feature, we again attach an auxiliary classifier after the recalibrated feature. Then we form the recalibration loss based on the logit output from the recalibrated feature, or P tilde minus. Recalibration loss guides the recalibration net to restore information relevant to the correct predictions. Our feature separation and recalibration module can be attached to any CNN model and adversarial training framework with training objective LCLS. It is trained with the entire network in an end-to-end manner by combining the adversarial training loss with our proposed separation loss and recalibration loss, each weighted by lambda separation and lambda recalibration. Now we will talk about our main experiment results and the evaluation of our method. For the baseline, we used various adversarial training techniques, including PGD adversarial training, traits, and MART. We evaluated our method on various datasets, including Cypher 10 and 100, SPHN, and Tiny ImageNet. We also attach our module on various models, including ResNet 18, VGG16, and WhiteResNet 3410. Our feature separation and recalibration module can be easily applied to any adversarial training techniques to improve the robustness against various attacks. We show the evaluation of our module when attached to PGD adversarial training. By simply adding our FSR module onto adversarial training, we can improve its robustness against various attacks by up to 4.65% under PGD 100 attack. The effectiveness of our feature separation and recalibration module is not limited to PGD adversarial training. It can also improve the robustness of other adversarial training techniques, including traced and marked. In addition to conventional white box attacks, our method still remains effective against black box attacks and auto attack. This shows that our method is also robust in practical cases. Now we show the results of our ablation study on the robust, non-robust, and recalibrated features that are generated from our method. We evaluated the robustness of each of these features via classification accuracy using each feature, the weighted KNN accuracy, and attention heatmap visualization. First, we can observe that our separation step can well disentangle the robust feature and the non-robust feature. The robust feature shows much higher classification and KNN accuracy than the non-robust feature. The robust feature also highlights regions relevant to the main object, while the non-robust feature highlights irrelevant regions. Also, recalibration step restores useful cues for correct predictions, leading to higher classification and KNN accuracy than the non-robust feature. The recalibrated feature also highlights regions that are relevant to the object. This is because it now captures useful cues that are restored via recalibration. With this additional useful information that are otherwise neglected via suppression or deactivation, the combined feature achieves the highest classification and KNN accuracy. Finally, we compare our method with conventional methods that deactivate or suppress non-robust activations. Our method outperforms these methods under the ensemble of various white box attacks and under auto attack. In summary, we have proposed feature separation and recalibration, which is a module that restores useful cues from disrupted feature activations.